So this is another video recorded by Ben Holcomb, Associate Professor in the School of Mechanical and Mechatronic Engineering at UTS. And in this video we've got a measurement going on here of the vibration of this 8-story tower. And in a previous video we showed the modal impact and subsequent modal analysis for a tower similar to this, the sister tower of this tower. In this case I have a single DC response accelerometer mounted to the upper level, the 8th degree of freedom for this tower, and I've got a shaker attached here to the tower via a stinger to the 4th level. I'm providing the shaker with a signal from the oscilloscope that's defined using the generator here with an amplitude of 1 volt peak to peak and presently a frequency of 26.7 Hertz. That's provided to the amplifier here, and I've got a gain set of about 50% on there with 0.7 amps currently heading through the amplifier to the shaker. Now I've chosen a value of 26.7 Hertz here because that was the value for the second mode that we extracted from the modal analysis from the other tower. Now the other tower is deliberately slightly different to this tower, so that frequency is probably not the correct frequency for the second mode. And what I'm going to do is I'm going to just adjust this frequency and observe the output from the accelerometer, the green signal, as I slowly increase the frequency, essentially trying to tune the mode. Now because the geometry of the tower is different, the dynamics are different, but as I get close to the resonant frequency, you'll see that the level on the accelerometer reaches a local maximum. So I previously estimated that to be around about 25.2 Hertz, which I can hopefully convince you of. As I go higher in frequency, the amplitude, which is being collected here by this peak-to-peak measurement, decreases. If I go back towards 25.2 Hertz, it becomes a maximum. Now this value will vary as a function of the temperature in the laboratory and other environmental conditions because the stiffness of the tower changes, but this is approximately a local maximum. And if we feel the vibration, in fact probably with the camera shutter speed we won't be able to see that one vibrating, but I can feel that with my finger. I can also move my finger down the tower, and at some point here between the 7th and 6th lumped mass I can feel a 0 vibration. That's the a nodal line for that particular mode shape. As I move down here I can feel vibration again, and there's lots of vibration here. Clearly the shaker is attached directly to that tower, so we expect some vibration, but that's the second mode for this tower tuned. If I then go back to my generator here, I can adjust the frequency to something approximately around 74 Hertz, which was again the value that we extracted for the third natural frequency for the sister tower. And again now you can see the frequency increasing. So 74.2 was the frequency, but I believe that because of the different geometry properties here, the actual resonant frequency is closer to 70.2, and you can see that acceleration signal growing significantly as I get to around 70.2 Hertz. So now I'm tuning that second mode. I've got a lot of response here, and actually we're looking at displacement, so it's harder to see the displacement for sure now, but I can really feel quite a lot of acceleration here. That's what the accelerometer is measuring, that's what we're looking at on the scope, and I'm feeling displacement. So because we're at a higher frequency we don't get as much displacement, but there's still some displacement there. And now I've got a nodal line approximately here between the 7th and 8th degree of freedom. There's vibration here, vibration here. Because it's the third mode, there's another nodal line here between the fourth and fifth of these two lumped masses. And that's consistent with what we would have observed in our modal analysis when we used our modal impact hammer to extract the mode shapes from these two towers. That concludes this video, which is about the tuning of modes on this 8-story tower using an oscilloscope and a shaker powered by an amplifier.